quizás ya hayáis leído un poco sobre su trayectoria. Kathrin actualmente está trabajando en el Centro de Investigación de IBM en Zúrich, en Suiza. Hizo su doctorado en el Helmholtz Center en la Universidad de Saarland y luego estuvo trabajando pues, en Cagliari, en Italia, y en la EPFL en Suiza. Y actualmente trabaja en el ámbito de la ciberseguridad. Entonces, pues bueno, puedes ir empezando.
Ok, bueno, muchas gracias. Sí, como ha dicho, si tienen preguntas en español, está bien, no sé si puedo contestar en español, pero... Okay, so let's get started. So today I want to talk to you about machine learning security in practice. So I suppose you've heard about machine learning, and maybe a little disclaimer before I start this talk. So during this talk I will sort of use the words machine learning and AI interchangeably. I think we all know that it's not the same thing at all. The reason I do this is because I did some work related to security, but also related to inquiring practitioners, how they use these techniques. And it's very hard to find only practitioners who use ML. It's easier to find practitioners who use both. And also security-wise, all of these techniques are sort of vulnerable. So this is why I do this, although obviously technically it's not quite correct. But so let's talk about machine learning security in practice. And something that you might be saying at this point is okay, so I've heard machine learning, I've heard security, but what the hell do you mean by in practice? And so I think we all know large language models, which is an example of AI or predicting text. And I think we've also heard about these jailbreaks and how they output things that are copyrighted, what they shouldn't do, and how they sometimes output just content which is at least safety critical. Whether it's security critical is more complicated to determine, but this is already a crucial and very practical question, right? So these systems are deployed and they're sort of causing problems. So there's a large agreement on that. But I think we also know that a lot of other types of AI are used in industry and products. Sometimes we are aware of that, sometimes we're not that much aware because it's running in the background. But the question is, okay, so what about the security of these systems? Is this actually a thing? And it turns out, yes, so there isn't only these security incidents related to large language models, but it's also for more classical models. So we asked 425 machine learning or AI practitioners in industry. So these are people who work at a company or at a startup, and they essentially implement a product that is related to AI, or they use AI internally to make predictions to inform decisions, for example. And so we got 425 of these, and we asked them, have you ever experienced a security incident related to your work, to your product that you do with AI? And 32 of them said actually yes. So we have witnessed something where someone tried to tamper with the system, someone tried to make the system output something wrong. And when we look at that, so we asked people to give us a short, high-level description of what happened. So now, if you've ever worked with human subjects, you have asked a vague question. Sometimes you get vague responses. Sometimes people are actually too scared to share the details with us, and they said I cannot disclose anything, but okay, something has happened. So from all these responses that we could look at, 8 were describing exactly what we define academically as AI security. So literally tampering with the input, causing a wrong output, or tampering with the training data, decreasing the performance of the model. So 8 of these were actually AI security incidents. So this is a thing that is actually already going on. And interestingly, orthogonally to the question whether this happens, there is already legislation covering that. So given that we are in Spain, you've probably heard about the UAI Act. And the UAI Act actually demands secure data and secure AI under a hefty penalty. Right? So we really have an incentive to, first of all, understanding what is going on, and second, learning how to fix it. How can we enable that companies use AI and it's actually secure? And this is actually what this talk is about. So first of all, I want to explain you, actually taking a step back and explain what I mean actually when I say AI security or machine learning security. And then second, I want to talk a little bit about where this disconnect is and why currently we're actually not able to fix the problems that actually are witnessed by practitioners who use AI in practice. And then I want to talk a little bit about how we can connect these two fields. Okay, so let's start with machine learning security, and I really want to start very basic here, because this is a very fundamental problem. And if you only understand how fundamental this problem is, then I'm already happy about like having achieved something with this talk, actually. So let's start really, really basic with a very, very easy example. So in machine learning, we generally have a clearly defined task. So for example, this could be distinguishing gibbons from pandas, right? So you have a panda class, you have a gibbon class. Mathematically, we usually denote this as y. And then you have an input feature. So like this could be an image, then it's very high dimensional. For the sake of this example, this is actually a one-dimensional feature, right? So here is more of the panda aspect of the feature, and here is more the gibbon aspect of the feature. And what we then do in machine learning is we essentially train a function from the data that we have, and this function actually maps this feature to a class output, right? So this is really just a basic classifier in one dimension, really easy. And then naturally the point of machine learning is to not actually just figure this out, but actually have some data and learn this in an automated fashion from the data. So far, machine learning, very basic. So let's talk about machine learning security. And there's something that I want just to very briefly emphasize. So there is a plethora of attacks on machine learning systems, depending on whether you do it at training time, at test time, what you tamper with, what you want to achieve from the perspective of the attacker. And today in this talk, I'm going to focus on a single attack. You could have the same talk about all of these other attacks as well. But I'm going to focus on this one, and the reason is that this is the largest body of work, and I've also published most in this area, but it really doesn't mean that this attack is more practical, or it's more relevant, or like it's really just like choosing this one attack, and you could do it with all other attacks as well. So let's talk about adversarial examples, also called evasion attacks. So let's go back to our classifier, and let's talk about what security means in the context of adversarial examples. So what the attacker could want is to tamper with the output of the classifier. So here it's a little bit, okay, where is the point, right? Because this is a very basic example. But if you think about malware classification, if you think about a system giving access to specific people by like an input image, right? This is really a security problem. And there's a lot of examples in classification where this can become relevant if you just arbitrarily can change the output of the system. So this is what the attacker wants to achieve. And what you can naturally do, if you look at this very basic function and you want to change the output, is actually mathematically very easily. So you look at the gradients and you actually start walking towards the other class. This can be done by using the gradient, right? So if you have high confidence and a gibbon image, what you would do is like you would walk towards decreasing the output of the classifier. This is everything like in terms of math, what we do when we compute these attacks. So essentially you take the original image and you compute the shift, right? This is the delta. So now here, so first of all, it looks very straightforward. But if you think about having an image or having language, for example, in an LLM, then this space here becomes highly non-trivial, very large. It's usually possible to find this change. In high dimension, it's usually very small. It's highly counterintuitive what this change looks like. You're going to see an example in a bit. That's essentially what you do. So you move this point toward the decision boundary. And what we add in security is this like arc minimum constraint, because naturally you can just repaint the entire image and then you have achieved what the attacker wants to achieve. But this is just not interesting, right? Because if you think about malware, you may want to preserve that the malware is actually malicious. And in the case of an image, right, you may want this still to look like a gibbon to a human that is checking the system. So there are some constraints here in terms of how much change is allowed. So let me show you like how this looks like when you actually take an image in high dimensional example. So this is the original image of a panda. You see it's correctly classified with high confidence. And this is the change that we get computing, like shifting this image towards the decision boundary. This is amplified, so you can actually see it. Because if you add it to the image here, I love asking that. Does everyone see a difference? I've never met anyone who did. But for the classifier, it's a big difference, right? So the classifier now is like super sure that this is a gibbon. And so this is an example in vision why this is a crucial problem. And maybe just to clarify that, so there is a related problem on large language models where you essentially get the same thing. By tampering with the input, you can sort of control the output of the classifier. And a simple example that I have here is an attack that works by metaphors. And what you actually can ChatGPT, or could ChatGPT at some point make output, is, so this is a copyrighted character, obviously, and it's also a children's character that posts on an action that's not good for children, smoking. So really, you can tamper with systems, like even more complicated ones like LLMs, to make it output something wrong. And the same, by the way, in the other direction. So you can technically also fool a statistical test into outputting something that it shouldn't be outputting by tampering the input data in a specific way. And now the question is, okay, so this is a problem. What can we do about it? And when we look at this classifier, and I said, okay, so I'm just pushing the point here to the other side of the decision boundary. So something you could say is, you know what, like, why are we even having this boundary? Like, let's make a buffer zone there, right? So at least when they have to tamper, they have to go further. Or maybe if a point is inside this area, I can say, you know what, I'm not sure what it is. So this could be a good idea. An alternative idea could be that I take the classifier and I'm highlighting areas where I simply haven't seen data during training. So analogously, you would say here, you know, I haven't seen anything here, I'm not certain what I should output here. And it turns out that this is actually something that exists already. So it's called Bayesian learning, and then like you have Bayesian models, and then you have two measures, you have confidence and you have uncertainty. So this is the confidence that you have that your classification output is correct. The other one is the uncertainty, or the certainty that you have in your output. And if you now take such a Bayesian model and you input adversarial examples, you could use those two measures and you can monitor them for these kind of malicious inputs. And what you would want, ideally, is that the confidence of any output is high. So if it is very confident, you may argue that this is less likely to be a malicious point. Or you want the uncertainty to be low, so you want to be very certain, because if you're very certain, the point is most likely not wasn't tampered with. And it turns out that if you actually do this, you see correctly classified data in gray is peaking around exactly the values as I said. The misclassified points or the misclassified adversarial examples are like scattered all over the place. So what you could easily say is, you know what, I'm putting a threshold here and I'm putting a threshold here. I reject everything outside of this interval. And then I've already dealt with like a lot of these malicious points. At this point, it's important to recognize that there's two different perspectives on AI security, on machine learning security. One is the perspective of machine learning. In machine learning, you have a task and you want to solve it. I just solved the task, right? Because I took the adversarial examples and I put the boundaries and now the input is rejected. But there's also the security perspective. So in security, we say I have a system and I want to protect it from an intelligent attacker. So the intelligent attacker is going to look at this and it's going to say, okay, what can I do to actually circumvent that? So I know that the boundary is here. So we generally give information about defenses to attackers because there is like a practice which is called security by obscurity. So like just hiding information from the attacker. This is considered a bad practice because if the only thing that's between you and the attacker is a little bit like of unknown, it's maybe very easy to achieve this knowledge, right? So we share this information in general. So what the attacker is very likely to do is going to adapt the attack. In this case, so I said, so we're using uncertainty and confidence. And what the attacker could do is that they say, okay, so I'm using the same crafting problem that I used before. So I'm minimizing this change. But like right now, I'm actually saying, you know what, I don't only want this to misclassified, but I want this to misclassified at high confidence, at a high certainty or at low uncertainty. So I want the model to be super secure, but still wrong in the output. And when we actually use this method to compute these points, what we get is this distribution. So we see that putting a threshold here and here is not going to save me from these inputs. Not if there's an intelligent attacker that really tries to get into the system. Okay, so let me summarize this first part of the talk. So machine learning security is something that unfortunately is very inherent to machine learning systems. So it uses essentially the same mechanisms that you need for training and that you need to like essentially write down these systems in the first place. So it's essentially the same mathematical principles. there's two perspectives on this. There's a machine learning perspective and there's a security perspective, so I will be mainly talking about the security perspective right now. This doesn't mean that the other perspective is like, it's just simply different. It's a different perspective on that, and some, like, depending on what you talk about, one or the other perspective may be more helpful. And lastly, defending machine learning models from these attacks, and this is true for many of the attacks, not for all, but for many, is inherently hard. And for most of the attacks, we currently don't know how to defend them, and we don't know if we will ever be able to defend them. So there are some approaches, like verification, but this doesn't necessarily scale to the models that we're interested in nowadays. So this is very important to keep in mind when we talk about AI security in general. Okay, that being said, let's look at the criticisms that we have found, like why, because this was very academic what I showed you, right? So these were research papers, it's like to understand why this is hard. But let's look at how this actually translates to practice. So if you talk about an AI model or a machine learning model that is deployed in practice, does what we know actually transfer to this? And like to argue about this, I'm actually going to use the same equation that I used earlier to introduce adversary examples, because you can use it very easily to sort of spot at which points it falls apart and it doesn't match practice very well. So the first one is this minimization problem. So if we look at security, this minimization problem comes from the mathematical framework of machine learning. And it doesn't necessarily translate well to security problems. So this is, for example, a screenshot of a phishing website. So it looks like the Google website. It actually doesn't, right? Because you see a couple of differences here. But it looks enough so that people would click on it and wouldn't realize that this is not the original Google mask. So using this optimization problem while being excellent, like in the context of like actually getting these points, isn't necessarily practical in terms of what you need to fool people or to fool systems. Right? So, and another difference is like if we generally talk about like minimizing this difference, then there is like this element of what is visible. So this is what you saw when you looked at the panda example, right? So this change wasn't visible. But you can actually have changes that is clearly visible. So here you have the black and the white square. So this is your perturbation. And this is the perturbation that is going to yield your model into outputting something wrong. And this works, not because it's invisible, but it works because every human being looks at that and says, like, this shouldn't have an impact on my AI, right? So like using this formulation isn't necessarily useful if you talk about practical adversary examples. Another example is the function or the models that we're considering when we do academic studies on adversary examples. So this is what is usually studied in a paper. So you take a model, you compute a perturbation, you test it. But this is actually how pipelines look like in industry, right? So you have different data sources, they're combined, the data is processed, and then you have a feedback loop. And it's unclear how this actually interacts with like either defenses or attacks and security. Then further, if we think about, and this is something I've implicitly talked about before, if we think about like how our point looks like and this delta that we add, then there's huge differences, right? So like I showed a lot of examples from vision, just because it's so nice to look at, so intuitive to understand. But if we look at code, like already knowing how this is represented for an AI system can be very hard, and this makes it a lot more complex or more easy actually to fool a system, right? Because here you may have different ways to translate code to a feature vector, and this enables different changes. And then lastly, if we look at this entire optimization problem, and if we look at like this desire to output something wrong, something that we have to keep in mind is that so I've been talking about attackers, and obviously the goal of security is to study attackers. But if we look at large language models and we look at these jailbreaks that I showed earlier, it turns out that a lot of end users are actually doing jailbreaks. And they do this out of fun, they do this out of curiosity because they want to understand the limits of a new technology. And this is a little bit the question, so what do we do in these cases? Like, do we consider this play, which is like fine behavior, like it's just, it's benign? Or do we say, okay, we also have to cover these cases because this raises the question of how do we want to deal with this kind of problem in the first place? And lastly, like in general, if we ask AI practitioners how they think about these type of attacks. So for example, adversary example, if we ask them if they think this is a relevant threat, and specifically, so some do, by the way, others say it's not relevant, and if we ask these people why they don't think it's a relevant threat, we can like really learn something about like these limitations as well in terms of what is research right now. So for example, a lot of people, when asked whether evasion is a relevant attack and they say no, say that's actually not relevant in their use case. And an example is if you're working in healthcare and you're having, I don't know, an assistant system to a doctor that tells you whether you have cancer or not, there isn't really that much incentive to have it output that you have cancer when you don't, right? So there is applications where this actually doesn't make sense. And this is important to understand in terms of, because if you have this problem and you cannot solve it in the first place, you should focus on the cases where it actually is damaging and there is an incentive to run this kind of attack. Another argument that is frequently brought up is like there's access control on the data. And that's something very subtle, right? Because they said, okay, so we're perturbing the sample, we're inputting it into the machine learning model. But to do that, you actually need to be able to submit something to the machine learning model. If this is a model that is internally used, maybe even in a physically constrained place, like there's no chance for you to ever run this attack. And then lastly, and this is something that we like had a little bit here as well, is like, is there even a motivation for an attacker to run this kind of attack? And these are all questions or aspects of like how practical these attacks are that we need to find a response to before we can say, okay, so this is the problem cases that we want to work on, and within these cases, these are the possibilities that we have to defend. So let me summarize these sections. So like we have this again, so we have these two perspectives, machine learning and security, and the optimization frameworks that we use usually to describe these attacks and define them, they are derived from machine learning. And while this is really cool because it just fits into any optimization routine, this doesn't necessarily help us to sort of do practical research on this kind of topic. Then secondly, and I think you saw this from the amount of criticism that I presented, is like there is a lot of criticism how practical this is. Now, having these like unpractical research isn't necessarily something bad, because this research still tells us something about the limitations of AI, but it still doesn't tell us anything about like how we can protect AI systems in practice, which again is a concern for like both legal reasons, but also because there's incidents already. And then lastly, so humans are very important key to actually understand that, to understand how AI is used exactly, which use cases are interesting for us, and to understand also how AI is used in terms of like access control and in terms of where an attacker can actually be motivated to target that. And this is what I want to talk about a little bit in the last part of this talk. So again, so these are like a couple of the questions that I just mentioned. So how is it actually used in industry or by end users, right? Because there can be different perspectives, there can be different people who are actually affected by this kind of attack. And then, like a related question, I said earlier, if you are not able to submit the data, there's no attack, right? So what kind of access rights do we actually have on systems that are deployed, right? It's something you need to know to understand if a system is vulnerable or not. And then again, like collecting incidents, so actually knowing what kind of incidents happen. So I said earlier we found evidence for 8 cases, but this is like a high-level description. It's a proof of existence of these kind of attacks, but really understanding well what happened, like what was the system, how was it secured, who was the one who tried to circumvent it. This is really needed to actually understand what is going on, what is the motivation, how to secure these systems. So let's talk about the access rights first. So I said adversary examples, so we craft the sample and we need to submit it to a model to actually be able to fool the model. So again, no access to the test data, I have no chance to actually conduct this kind of attack. So rephrasing, if we want to attack via evasion adversary examples, what we require is at very least, the ability to submit test data. And then ideally, if you think about this optimization problem that I showed, you have actually access to the model, you have the gradients to compute this kind of perturbation. So, and what you see here on the bottom is actually a sample of 271 AI practitioners, so people who work with AI. And what we essentially did is we asked them, do you give access to your test data, do you give access to your model? actually also do you give access to your training data? This relates to what I said in the beginning. You can do this for pretty much every attack. So this is the percentage of people who said we are giving access to both the model and the test data points. So you can see the model there, you can use it, you can tamper with the data, you can submit it, you can get your wrong output. So this is actually something that exists, right? And if we now say, okay, so this is very little people, right? So if you only consider the ability to submit test data, then this is about a third. So about a third of the systems that are currently deployed in companies actually give you that ability. So you can submit a test sample and you can fool the system. We still don't know what kind of application that is, if it is security relevant, if it is only deployed for yourself. So that's something we don't know, but we know a third of these systems is vulnerable to evasion. And then we have like this part, so these are cases where people don't give anything, like don't give access to anything, like neither test data nor the model, not the test data actually. And then we have here like another fraction of people who either didn't respond to one of the two or who give only access to the model. So if I have only access to the model, I mean like I can craft something, I can maybe copy the model and run the attack, but I cannot really like submit something and get like a bad output on their side. But what is relevant is understanding like a third of these models is actually vulnerable. And so something you might say is like, okay, but I don't have model access, so how can I attack this? And I think it's intuitive if we know a little bit about math. We know that like if I can only query the model, something I can do is I can repeatedly query this model and essentially like approximate the gradients. So I don't need to compute this equation directly on the model, but I can essentially query a couple of points with changes and I get a gradient and I can just perturb the point anyway. And so this already exists, like as you can see from the title, so it's called Black Box Adversary Examples. And these attacks are generally based on queries. Because to get the gradient, you need to query repeatedly, and the question is, okay, so how often do you need to query, and how realistic is this actually? So how many queries do you generally get if you look at an industrial model? So this is the distribution of research. So maybe as a quick disclaimer, so this is a survey, and I think they covered like 22 or 23 black box papers. But this is the amount of queries that they reported, right? So most of the papers use unconstrained amount of queries, and then you see another peak, which is between 100 and 1K queries. And this, by the way, is very intuitive, because first of all, you want to make the point that this is possible in the first place, which is most of the work here. And once you have established this as a research direction, you would try to sort of get the query number down to interesting numbers, right? So this is essentially what we see here, like the normal development of a research field. But if we match this with the queries that are actually allowed in industry, then what we see is again, and this is pretty much the same thing that we saw in the previous slide, so most cases, like no queries are allowed at all. And we see second most frequent, actually this is a little bit higher than the other one, is unconstrained, where here actually it's also an open question whether this is necessary. So this potentially can always be reduced. You may say, okay, you're not allowed to do infinitely many queries anymore, you can only do 1K. And essentially what we see is like there is a mismatch because many models allow only very few queries, whereas most attacks like use a lot of queries. So this is also where we need to adapt our research and be like, need to do realistic security assessments, essentially we would need here. So these works can help us understand how vulnerable these models are and how we can secure them, right? So we need to sort of get this research more into the direction of what is actually needed. All right, so what I previously presented to you is actually a vulnerability. So this is the possibility to exploit something. It's an attack surface. This doesn't mean that there have been attacks or there have been exploits, but it's only the possibility that this happens. And the question is a little bit, so which incidents occur? So is this actually exploited? Which systems are exploited? Like in which industry are these? And something that we're currently working on is trying to propose an AI security incident reporting framework. Because, so I don't know if you've heard about, someone has heard about CVE here, or CWE? Okay, one person. Okay, great. So this is the system or the database that is currently used to collect cybersecurity vulnerabilities. So if you find a flaw in a code that is exploitable, you essentially write this up, you report this to the institution, they verify it, and then it's published. Simplifiedly speaking, because naturally this is first of all communicated to the provider of the software where you found it, and then they have a certain time window to fix it. Because obviously you don't want to publish a vulnerability that can be exploited. So we have this infrastructure already, but there is a couple of reasons why it is not going to work very well for AI. And one reason is, for example, as I just said, so you share the vulnerability, you share the line of code where the vulnerability is. But this is very hard for like AI, right? You cannot just share the data and the model. Maybe this is IP protected. This could be very private. If you think about healthcare, you cannot just share patient data. Your model may be your asset. This is the case for a lot of startups. So they have this model, and the model is essentially their product. And then we also have a legal problem, because right now AI models are not protected as IP. So the moment that I share the model, I cannot protect it legally anymore. It's only shared by keeping it secret. Another difference is that we essentially, and that's like the first part of my talk, is we know that these models are vulnerable. The question is how they are exploited and who exploits them. It's not, or like whether they are exploited, it's not how, right? We know how, we know all these attacks. Maybe there's a couple of attacks that we don't know yet, but so essentially there's a lot of differences that like sort of demand that we have a specific incident reporting framework here. So let me just introduce like what we think could be a good idea to report this. Because if you think about CVE, that's very abstract. You're essentially only sharing the vulnerability, and then like this can be reproduced. For AI security, this is way more complicated. Okay, so the framework we suggest essentially has a part where you just collect the meta information. This is just about having a name essentially to talk about this incident, maybe collecting who is reporting it, which company is reporting it, depending on how anonymous you want this to be. Then there is a second part, which is the AI system information. Because naturally, if you're reporting a vulnerability, you may want to know, I don't know, which exact version of ChatGPT you're talking about, or which classifier you're talking about. What is the surrounding? How does the pipeline look like, right? So that's what I said earlier. We need to understand all these elements to determine how the attack worked and why it wasn't prevented, or whether it was prevented partially. And this is important to understand also how this carries over to other systems. Then there is another part which is about incident information, and this relates, for example, to access rights. So like who had access to the system, how was the sample submitted, maybe even like, so what was the root cause for this exploit, so what enabled actually running this attack. Then lastly, and this is something more researchy and more like in the very long term, is like what kind of damage was caused by that. Because if you think about an autonomous vehicle, so this can physically harm a person. If you think about, so there were some issues with an AI that was deployed in Netherlands, I think, where people were denied their social benefits. So this is a financial damage or financial harm. So collecting this can be very important to understand which kind of systems are like targeted and how to deal with this, and also how to prioritize research. And then lastly, it's just an appendix to sort of add either further information that wasn't that we didn't inquire for before, or it's also to connect it, because there's other databases that collect ethical incidents, like the one that I just mentioned with the social benefits, right? So it may be interesting to connect these incidents, or even connect this to CVE, because you may have a case where a cybersecurity vulnerability is connected to an AI security vulnerability to exploit a system. So let me come back again to the bigger system, so to the bigger picture. So I was talking mainly about adversary examples in this talk. So again, there is like many more attacks, like about like leaking the data or leaking the model, or attacking during training time and so on. And all of these essentially have the same issue, that it's very hard. We don't know necessarily how to defend against them. We don't know in which cases they actually happen in the wild, and in which cases they could be relevant as well. And then, like on the other hand, we also have like, so the application I was mostly talking about is classification, right? Because it's easy to illustrate in terms of images as well. But essentially, as I said, so any other application of AI or machine learning is also vulnerable, right? If you think about things, like I gave the example of statistical tests, you can also have data mining, right? It doesn't even need to be supervised. You can even attack reinforcement learning. So this is really a very, very big general problem. And for none of these, essentially, we really have a practical understanding how to secure it, or when this is even critical, or when this is used in industry and for what it is used, which would all be very important to understand security and actually fix it. But yeah, the reason that I talk mainly about this example is because I published most in this area and not so much in the others. Okay, so let me summarize. So I hope you understood this difference between machine learning and the security perspective and why this is relevant in this context. And then I hope you really understood how deeply these vulnerabilities are inside machine learning. So it's not like in cybersecurity where you have a bug, where you have a code line where you can go. You cannot just fix it. It's something we're going to have to live with and have to figure out how we can fix it in a specific practical setting or for a specific application. And this directly translates to defenses because it may not be possible to fix any or some of these applications at all. So the solution may actually be to not use AI in some cases where we cannot secure it. Then in the second part, really this difference between the two perspectives and what this means, that we need to think more in terms of security, at least when we want to secure real-world systems. Then there is this existing criticism, so this has been acknowledged, and there is some work recently trying to fix this. And as you saw the last part of my talk, so there is some recent work on how to tackle these real-world incidents by at least a couple of researchers, so it becomes more common. And in some fields, for example, related to autonomous vehicles, there's also a tendency to sort of look at more real-world attacks, so actually not evaluating an attack only on a digital system, but actually printing the examples and testing it on a real Tesla, for example, and showing that this also works. So there is this understanding in the community that we need to address this in more practical terms. Then lastly, as motivated in the very beginning, so we need a solution for these systems, we have legal requirements, we have practical requirements, and also just in general, we may want to fix this before it becomes a real problem, right? If you think about how cybersecurity developed in the past 30 years, so some of the findings that we had 2 years ago are sort of similar to what was found in cybersecurity 30 years ago. That doesn't mean that we are going to go the same trajectory, but it means that we are very much at the infancy, probably both on the attacker side, but also on the defender side. So this is a good moment to start actually solving that at its root before it becomes a problem. And then again, so I talked about some unknowns here already. So we don't know which attacks occur how often. We know that they do exist, but we don't know much more details. We don't know how to implement practical defenses because we tend to test them on very basic models and not on practical settings. And then again, there is a huge human factor. So sometimes even though organizations know that they should implement AI security measures, they simply don't do it. And this is delegation of responsibility, or it's simply maybe not having the education that is required. So that's something that we're researching currently. But this is all questions which are currently still open. Okay, with that, I would like to thank all my co-authors, because obviously I'm not alone to do, I'm not able to do all this research by myself. And feel free to ask questions. Yep.
You have some questions? Preguntas?
Okay. For me, it's a bit difficult to understand some of the things that you presented, but it seems, for example, thinking in large language models, you talk about autonomous vehicles, but you can think also in language, perhaps. You talk about a function that you have to find, or some kinds of examples you have to find in order to just the system gives erroneous output. But for example, thinking in very complex scenarios like autonomous vehicles, it is pretty difficult to find, or for example, with some kind of examples that you can use in order to get the system to give the erroneous output. It's very difficult, for example, to get that the system gives some erroneous output, or to compute the delta that you have to use is quite easy in some cases. I don't know. I don't understand that.
Okay, yeah. So let me give you two examples, because one is you just asked about large language models. So there was a case related to large language models, and maybe a disclaimer up in front. So we don't know if this was intentional manipulation or whether it was just a benign error, which is also a problem that we face in AI security. But there was a case where a client interacted with the chatbot of Air Canada. And the client interacted with the chatbot and essentially explicitly asked if I'm buying this flight in this context, can I get a refund? And the chatbot essentially said yes. So the client bought the flight and asked for the refund later on. And then Air Canada said, no, we nowhere say that we are giving a refund under these conditions. And then there was a court case, and essentially what the judge said is like, you're liable for what your chatbot outputs, so you have to give that refund. Although the refund was never specified somewhere on the website. And this is a case where, like, if you can manipulate the chatbot into outputting this, there can be legal consequences for a company, right? And then, like, I think the question was also like, how difficult is it to find these kind of like malicious outputs? And so maybe let me go back and stay in the area of LLMs. So this output was actually rather easy to achieve. It relies on using two metaphors, because what ChatGPT does, or at least did in that moment, so this is from last year, they filter. So if you say, I want an image of Mickey Mouse that is smoking, this is not giving you any output. So what they did actually is they used two metaphors. They used the metaphor for Mickey Mouse, which I don't know if it's known in Europe, I think it's more an American thing, which is the place where Super Bowl players go after they win the Super Bowl. No, football players go in after they win the Super Bowl. This is a common meme, right? And this is a meme that translates to Disneyland. So that was the first part of getting Mickey Mouse into the image. And the second metaphor is let this character do an activity that was legal in bars 30, 40 years ago, but is not legal anymore. So you just need to think about a representation that is likely to avoid the input filters that are provided, but it's not hard to get this kind of input. So this is for images, and then you said for autonomous vehicles. Essentially, so the problem you have is when you go from a known attack. Let me go back to an image. So this perturbation, for example, it's computed on a specific classifier. Yeah. So this is easy, right? You have the classifier, you compute the perturbation, you essentially use this equation, done. If you want this to work on another classifier that you don't know, all you essentially do is you change this for the classifier that you use as target to be more and more confident, because it turns out that all of these classifiers are roughly the same. Now, it's an independent research question why this is the case. It could be because we're all using the same vision data sets for training. It could be because the manifold for images looks in a certain way, so you cannot get too far away from that. But so essentially, like, these two models are always going to be similar. And if you keep on crafting and keep on increasing the confidence for, like, the target model, which has absolutely nothing to do with the second model in the car that you don't know because it's proprietary, you get a perturbation which is stronger than a perturbation that you would get on the same model to fool. So that's the first thing. So you need to increase the strength to have it carry over to a model that you don't know. And then you also need to increase the strength independently, because you essentially have to print this perturbation, and then you have to mount it for the car, right? It's like printing it, because in the digital space, the pixels directly go into the model. But if you print it, you're losing perturbation on the way of printing it on paper. So you essentially increase the perturbation and you mount it. And in that sense, it's not really difficult. Obviously, there's always a little question mark whether it is going to work on the car or not. You cannot know that. But if you craft a lot of these examples and you put them up in a town, it's very likely that the car is going to misclassify some of them, yeah. So this is actually what I said. So it has been shown that that these attacks transfer to Teslas or to other cars, like that use this kind of algorithm inside.
Yeah, I have another question. For example, there are some cases in which you can just attack the train data in order to, for example, see you are using some application for coding, for example, in order to the code that you generate, for you put a backdoor or something like that in the code. There are cases, it will be possible. I understand that it will be possible, but there is no case about that, or?
Yes, and maybe. So maybe because we know that, like, and this is also part of the survey which I showed, where we asked, like, where I depicted whether it's possible to attack these systems. So people use a lot of publicly available training data from the internet. And ChatGPT is a good example, right? This is why it is able to output these horrible statements, which I think mined from, like, 4chan or something like that. So this is a case of maybe. And in other cases, so this is actually something of these 8 cases that I said in the very beginning. So there was one case where someone reported, so they had, like, essentially a division of workers that were working on labeling the data. So they were labeling the data and then they were using it in training. And for some reason, and really we don't know the details there, like, some of these workers got scared that they are replaced if the AI is performing very well. So they started to assign wrong labels. And then obviously the performance on the training process didn't work any good, right? And this is an example of a poisoning attack, although, like, there is a big ethical aspect, obviously, that we have to consider here. But yeah, this is a report of such an attack that we have.
Okay, thank you.
Yeah.
Any other questions?
Well, thanks for your talk. My question is, your talk was about how can AI be attacked, but how can AI make more robust cybersecurity systems? Do you have any thoughts on that?
Yeah, so this is not an area that I work in a lot, but yeah, you can use AI to help people as well, right? So if you think about incident response, like cybersecurity incident response, like a big use case of AI is actually to have these, I don't know, 10,000 incidents per day, and then you can actually, the AI can say, okay, like, I don't know, maybe 9K or 9.5K of these are actually nothing that we have to look at because this is something that we saw yesterday and the day before. So it's actually reducing the workload of the people who work in incident response, and they have to look at less cases. This is a good example of how you can use AI to help. Or, like, if you think about monitoring network traffic, like this ability to look at something and say, like, this is normal and this is exceptional. It's a good example. However, like, there as well, you have the problem that people can attack these systems. And then you have an incentive to pass something as don't look at this because this is not good, right? So it's like, it's sort of connected. But yeah, there is definitely potential for this, yeah.
Okay, thank you very much.
More questions?
So, what would you say are the main ways to make this machine learning more robust? Not just to use AI for security, but to make the models inherently more robust than they are. Because you said these security issues are inherent to the models.
Yeah.
Is there a way to make them inherently more robust? A little bit more robust, at least?
Yeah, so this is very dependent on the application. So one application that I really liked working on was trajectory prediction. So this is a 2-dimensional task. So you essentially have a grid and the car is encoded as a point that moves along that grid. And you have other cars which are encoded as points as well, and then you try to predict how they move, and then that gives you a hint how you move. So this is a task that is used within an autonomous vehicle. And this is, I'm bringing up this task because, like, the issue we have in vision, right, is we have so many pixels, it's so hard to know what someone could do. And in trajectory prediction, we only have this 2-dimensional grid. And we have physical constraints on how a car can move, right, because it's not going to beam itself in 1 second, 2 meters to the left and then back. So this is an example where you can at least, like, figure out a lot of adversarial perturbation simply by enforcing these constraints by saying I'm not looking at vehicles that are behind me because I don't need them. So we tested backdoors there. So training time attacks, and you could actually use a car behind to attack the system in front, and that's like something you can easily avoid. So you still have then vehicles that you can use to mount an attack, but it's very much harder if you have these constraints. So like again, there's no necessarily security. You could try to think about implementing verification, and then upscaling verification would also be an option to make this more secure. But yeah, like I think we can only look at like applications and how they are actually used in practice, and then like figuring out if there are constraints that allow us to make something more secure. But in general, it's yeah.
So it's a case-by-case solution.
Yeah, I would say yeah.
Okay, thank you very much.
Any other question? No. So thank you very much, Kathrin, for your interesting talk.
Well, thank you for having me.